So this is a joint work with Robert Ikeda and Professor Jennifer Widom from Stanford University. So let me start with a brief motivation. So today, it is extremely common to use MapReduce workflows for large-scale data processing tasks. So just to clarify, a MapReduce workflow is a directed acyclic graph whose nodes are MapReduce jobs, and edges represent the flow of data. So there are various ways to program MapReduce workflow. You can use Hadoop directly, or there are popular tools like Pig or Hive that create MapReduce workflows for you. So despite these great tools, programming MapReduce workflow is not necessarily easy. And I believe one of the reasons is that debugging these MapReduce workflows can be quite difficult. So as an example, let's say you just ran a complex MapReduce workflow and found out your output data has a suspicious output element, right? So you want to verify or debug this element. The chances are it'll be very hard to come up with a small test data set that can reproduce the same problem. But you don't want to work with the entire input data because that'll make the iterative debugging process very time-consuming and inefficient. So how can provenance help? So the term provenance in general means where data came from, how it was processed or evolved over time. In this context, we are looking at fine-grained provenance of data elements, or key value pairs. So you can think of our provenance as a bipartite mapping between input and output data elements. So what can we do with this provenance information? We can support two basic operations, backward and forward tracing. So backward tracing finds the input subset that contributed to a given output element. And forward tracing does the opposite. Given a particular input element, it finds which output elements are derived from this input element. So our goal in this work is first to capture provenance with as low overhead as possible in terms of running time, space, and the programming effort. And second, to support very efficient backward tracing operation. So in the rest of this presentation, first of all, I'm going to define MapReduce provenance, and we'll see an example of that. And then I'll describe the ramp system in some details and go over the experimental result. And finally, I'll give you one more realistic use case, which is a provenance-enabled Pig running on top of ramp. So let's define MapReduce provenance. So before we get to the provenance for the entire workflow, so in this slide, I'm going to focus on each of the mapper, reducer, and combiner. So for mapper, as we know, mapper produces 0 or more output element independently for each input element. So we define the provenance of an output element as the input element that produces the output element. So in this case, provenance is always a single input data element. On the other hand, reducer produces 0 or more output element independently for each group of map output element with the same reduce key, right? So we define the provenance of an output element as the entire group of map output element, of course, with the same reduce key that produces the output element. Finally, for the combiner, it's same thing for the reducer. It's the entire group of map output element with the same reduce key is the provenance of an output element in combiner. So let's look at MapReduce workflows. So our definition for MapReduce provenance is a straightforward recursive definition, which means that starting from the final output element, we'll keep applying an appropriate definition from the previous slide until we reach the initial input data set. Okay? So having defined the provenance in this intuitive way, So there is one obvious desirable property which we call replay property. So that is, if we rerun the entire MapReduce workflow with the provenance of an output element as input data set, can we see the same output element in the result? The answer to this question is usually yes, but not always. So if you're interested in the exact condition when this property does or does not hold, you can take a look at our research paper from CIDR 2011. For now, it's fair to say in most cases, this replay property does hold. So that was a definition for MapReduce provenance, and here is an example using Wordcount. So in Wordcount, each input data element corresponds to a line in the text file. So we have two input files, one with 3 lines, the other with 2 lines. And we apply mapper to get a bunch of word, one key value pairs, and apply combiner to get the aggregation for each file. And then finally, the reducer produces this 6 key value pairs for each unique word. Now, let's look at the provenance of an Hadoop, 3 key value pair, right? So according to our definition, the recursive definition, first of all, the provenance in terms of the input to the reducer is the group of map output element with the same reduce key, in this case, Hadoop. So the provenance is Hadoop, 2 and Hadoop, 1. So we do this same thing for the combiner, and we get 3 Hadoop, 1 key value pairs. And finally, for the mapper, we get 3 lines, each of which contains the word Hadoop in it. So this is the MapReduce provenance. And let's take a look at the replay property. So we basically rerun the same word count job with 3 lines as input data set. So we basically the same thing for mapper, combiner, and reducer. And we can see the Hadoop, 3 key value pair in the result. So this is case where the replay property does hold. Okay? So that was for the MapReduce provenance. And let's take a look at the system overview. So our RAMP system is built as an extension to Hadoop version 0.21. It supports the MapReduce jobs written in the new MapReduce API using the context object. So our code is organized as mostly as a library, but there are a couple of minimal changes in the core part as well. So overall, our system consists of the 3 parts. So first 2 parts will work together to capture provenance for single MapReduce job at a time. So as a result, each MapReduce job will have its own provenance output. And the third part will trace provenance of a final output element all the way into the initial input element across all the MapReduce jobs in the workflow. So the first part is generic wrapper implementation. So when the ramp captures provenance, there are several wrappers around the user-supplied code, such as record reader, mapper, combiner, reducer, and record writer, and partitioner, and so on. So we will get to the details of how these things work in a couple of slides. But for now, the main benefit of this wrapper-based approach is that this is transparent to both to Hadoop and to the user. So from Hadoop's point of view, what you get after wrapping all of these components is another Hadoop job. So we can easily retain the nice properties of Hadoop, such as scalability, fault tolerance, and so on. So from the user's perspective, user need not be aware of provenance capture when writing MapReduce jobs. For example, we store this provenance information separately from the original output so that our wrappers doesn't break the entire workflow. The second part is pluggable schemes for provenance capture. So we have 2 schemes, one for element ID and one for provenance storage scheme. So we need element ID because we are storing provenance in terms of input element IDs and output element IDs. But obviously, Hadoop does not have notion of element ID, so we added this to record reader and record writer. So for example, record reader will give you the current key, current value, and the current element ID, all right? And then there is a storage scheme for provenance. Well, obviously, you have to store this provenance information somewhere. For that, we are reusing the output format. So by providing these two schemes, you can apply our provenance capture to any MapReduce workflow. Finally, the third part is a provenance tracing program, which is a standalone Java program that heavily depends on those two pluggable schemes. So that was the overview. And now let's take a detailed look at provenance capture using wrappers. So here is a diagram without provenance capture. In the map phase, there are a record reader and mapper. So with provenance capture, both record reader and mapper are wrapped by our system. So the goal in the map phase is explicitly tagging each map output key value pair, here km, vm, with the provenance information p that is an input element ID assigned by the record reader. Okay? So other than this element ID information p, the input output of both record reader and mapper are exactly the same with or without provenance capture. So after shuffle phase, for now, let's say there's no combiner. Adding combiner is very straightforward. So after shuffle, here's a reduce phase without provenance capture. And with the provenance capture, again, both reducer and record writer are wrapped. You can see the map output are now tagged with the provenance information. So in addition to the original output, we are going to store two more output streams for provenance. The one is reduced provenance, which is from the output element ID Q to the reduced group ID KMID. Okay? So this is reduced provenance, and there is another one, map provenance, from reduced group ID to all input element IDs. So the reason why we are storing both reduce and map provenance in the reduce phase is that this way we can basically gather all the provenance information corresponds to the same reduce group in the same place. So that will speed up the provenance tracing procedure. So once we have these two more output streams for provenance, you can imagine how this provenance tracing program will effectively join these two streams to get the mapping between input element IDs and output element IDs. So for the default scheme for pluggable schemes, right? So the most common case in Hadoop is the input and output in the HDFS. So we'd like to support this case very efficiently. So element ID in this case is a combination of file name and offset. So this combination will uniquely identify any record in file. So it also has a couple of nice properties that will further speed up the provenance tracing program. For example, as you append more elements in the file, your element ID will increase. So basically, later we can use binary search. And there is a provenance storage scheme, two output formats, one for the reduced provenance, one for the map provenance. In this specific case, reduced provenance is from the output offset to the reduced group ID. So we don't need output file name because each output file will have its own provenance, its own reduced provenance. And there is a map provenance from the reduced group ID to the input file name and offset. So there are a couple of optimizations to reduce the file size. So with that, let's take a look at the experimental result. So we did performance experiment on EC2, a 15-node cluster. For detailed Hadoop configuration, again, you can take a look at our research paper. Basically, we use two different MapReduce jobs, Wordcount and Terasort. So these two jobs have very different characteristics. The Wordcount is a many-to-one transformation, and Terasort is one-to-one transformation. So for both of them, we do three different input sizes, 100, 300, and 500 gigabytes. So here's a rather complicated graph for word count. So from the left, we have execution time, and map phase time, and reduce phase time. And there is a space graph, which is an output, map output data size. And there is an intermediate data size, which is after applying combiner and map output compression. And finally, there's an output data size. Okay? So as you can see, for the word count, almost all running time is spent in the map phase. And combiner is very effective. We are using 8,000 random English words. So intermediate data size and final output data size are both very small. So with the provenance capture, so on top of these blue bars, the red bar indicate the time and space overhead for provenance capture. So you can see in the map output data, there are quite a bit of overhead in terms of space. This is because in the word count example, each map output key value pair is rather small. It's like 20 bytes. So the provenance information, the input element ID, is relatively large. So we have some space overhead here. And then the combiner is not effective to reduce the provenance information size. So we have some data in the intermediate and final output data. So overall, the execution time increased about 76%. So same thing for the Terasort. In this case, Terasort, each record we are sorting is 100 bytes. So the effect of provenance information is smaller than the previous case. So overall, time and space overhead are about 20 and 21%. So to summarize the experimental result, provenance capture has some reasonable time and space overhead. For word count, 76% time overhead, and Terasort, about 20% time and space overhead. And for the provenance backward tracing, so this is one piece we didn't really try super hard to optimize. But to give you some ideas, for word count, tracing one output element took about 5 minutes for 500 gigabyte input data. It sounds like it's very slow, but by tracing one output element, we'll fetch about 6 million lines in the input. For Terasort, it takes about 1.5 seconds. Because it's one-to-one, it's pretty fast compared to the word count. So finally, I'll quickly give you one more realistic use case for our system. So we basically modified Peak so that Peak can utilize our system to capture provenance. So we started with Peak 0.8 and added this element ID scheme based on file name and offset. That was about fewer than 100 lines of code. And for provenance storage scheme and tracing program, we can just reuse their default ones. So here's an example Peak script for sentiment analysis over Twitter data. So we have two input data sets, a bunch of tweets from 2009, and we have about 500 movie titles from the IMDb. For each tweet, we have a classifier, so we use that to infer a 1 to 5 star rating for this tweet, and then generate all n-grams from the tweet, join them with the movie titles to extract which movie this particular tweet mentions. And there are a couple of additional steps. involving filtering and outer join. And finally, our output data looks like this. So movie title and rating. And there are a number of tweets from November 2009 that rated the movie as the rating in the second column, and the number of tweets in December. So the script looked like this. It's about 20 lines of code, compiles into 4 MapReduce jobs by peak. So here is a screenshot of a backward tracing. So in the background, you can see our output data. For example, there is one tuple. The second one is avatar, 1 star, 2 tweets in November, 7 tweets in December, right? So when you click this record, you can see the provenance. So here we have exactly 9 tweets, 2 from November, 7 from December, that rated avatar as a 1 star. So you can see some tweets are complaining about the plot or bad story and so on. So before we conclude, so there are a couple of limitations in our system. So one comes from the definition of MapReduce provenance. So when we define the provenance for reducer, we define the provenance of an output element as an entire group of map output element with the same reduce key that produces the output element. So essentially, we treated reducer as a black box. So if your reducer is a many-to-many transformation, your provenance at the end may contain more input data element than you desire. Right? For example, if you sort a bunch of records, and this record has some duplicates, right? Then if you backward trace one element, you might see multiple input data elements with the same sort key. So same thing could happen for the joining 2 tables based on which join algorithm you are using. Finally, because of a wrapper-based approach, if your MapReduce job does some hacky stuff, like if your mapper buffers something so that overall this mapper does not apply independently for each input data element, for example, then the captured provenance might not be as meaningful. So that was a limitation. And to conclude, RAMP transparently captures provenance with reasonable time and space overhead. And through the backward tracing, it provides efficient means of drilling down or verifying the output element. So that's all I have. And thank you very much. And I'd love to take any questions.
Have you looked at exception and error handling? Because I know sometimes, at least with my code, a null will show up somewhere I didn't expect it to, and that will result in an exception. And it would be great to be able to trace back exactly what input elements came to create that exception.
So our provenance is a purely data-based. So we assume your MapReduce program works well, except in terms of data, it has some suspicious element. So currently, we cannot deal with that.
For the mapper buffering problem and the reducer many-to-many thing, did you consider any sort of like manual instrumentation API where people would be able to propagate provenance in their code?
So you can sort of do the same thing without this automatic wrapping approach, right? So you can basically manually tag your map output key value pairs with some provenance information, right? To get the provenance output at the end. But using our approach, because it's automatic, we have to assume certain things. And that's, in your case, you have to do it on your own.
So I had a question, and you sort of mentioned, but I didn't quite catch the reasoning for it. And what was the reason for your overheads being lesser in Terasort versus the word count? And a related question to that would be, what are the factors that affect your overheads? Is it the input data sites, the number of maps? Have you done any more analysis on that?
So let me repeat this. So word count each map output key value pair is basically one English word and a count. So it's about 20 bytes of data, right? So if you tag this map output key value pair with the provenance information, well, that's going to be about 30 bytes or something, right? So your overhead, because of adding this provenance information, is, let's say, 50%, right? But for the Terasort, your map output key value pair is exactly 100 bytes. So adding 10 more bytes will be the overhead of 10%, right? So, and then there's one important thing is, for word count, you can use combiner. And combiner is very effective in reducing the intermediate data size. But Terasort doesn't have combiner, right? So because of those two reasons, Terasort, we experienced a lower space and time overhead, or word count is higher.
So the intermediate data sizes for the map provenance, so the compression, I mean, if you use compression, I believe your provenance information cannot be compressed very well. I mean, so your compression rates for the intermediate data sizes will actually go down a lot if you add provenance information. So have you experimented with that, and do you have any numbers on that?
So the graph, to produce that graph, I used LZO compression for map output. So if you carefully see the graph, the red bar is actually a little bit smaller for the intermediate data set compared to the map output data set.